In this video, we're going to find the volume of the solid generated by revolving the region bounded by y equal x, square root of x plus 1, and y equals 0 about the y-axis. Now this is the same region that I had in another video. In that video, we found the area of the same region. So what we did there, we found the points of intersection of the two. So we solved this system here by setting the two y's equal to each other. So x times the square root of x plus 1, set that equal to 0. Y equals 0, of course, represents the x-axis. So set each factor equal to 0. Since we have product, x can be 0, or the square root of x plus 1 can be 0. If we square both sides, I get x plus 1 equal to 0, which means x is equal to negative 1. The y value is always 0, so this will be 0 here. And when x is 0, the y value is always 0, because this is where this graph intersects the x-axis. So the curve intersects at minus 1, 0, and 0, 0, and it's below the x-axis in the interval from negative 1 to 0. And we created the graph of that one, and I'll show you in a minute. But what we want to do is this information, just to let you know, we're going to use the shell method. If the axis of revolution is vertical, then volume of solid revolution is equal to. If the axis of revolution is vertical, the volume of solid revolution will equal to this formula right here. So this is generated, of course, from the volume of a shell. 2 pi, the limits of integration from a to b, p times hx dx. And this is where the dx will represent the width of the rectangular strip. So we form a rectangular strip, and the thickness is the thickness of the shell. The h is the length of the rectangle, which corresponds to the height of the shell. And p is equal to the distance between the axis of revolution and the center of the rectangle, which gives you the radius of the shell. So now let's look at what we have. So here's the graph, or part of the graph, at least the part we're looking at. This graph actually goes up this way, like that. But we're not interested in that part. We only want the region that's bounded by the function they gave us and the x-axis, which is y equals 0. So here's what we have then. We form shell method again. The rectangular strips that we use right here are going to be parallel to the axis of revolution, which is the y-axis. So again, there's my rectangular strip that I'll be using. And these, of course, are real tiny. Hundreds of these tiny ones along this area here. And then the integral is going to go from negative 1 to 0. I have it right here. And the value of p will be the distance from the axis of revolution, which is the y-axis, to the center here. So it'll be the distance x, but it's going the negative direction. So that's why I have it 0 minus x. So the distance to that center of that strip will be 0 minus x. And then the height of this strip, the width of this strip here is going to be dx, going horizontally. So we're integrating with respect to x. And then the height of this rectangle right here is the distance from here to the x-axis. So let's call that 0 minus the curve. So that's why I get this, 0 minus the function. And then what I did is this will actually be then minus x. This will be minus x here, this will be minus x here, and this we just multiply this out. So let me rewrite this. So this becomes this. And of course x times x will give me x squared. So we wind up with this then. So all we have to do then is find the integral of this expression here in terms of x, and then apply the limits of integration. Evaluate it at 0 minus the value at -1 multiplied by 2 pi, and that gives it to us. That's one way to do it. Now I'm going to use a u substitution. I did the similar thing when I did the problem involving area. So I'm going to let u equal to x plus 1. So this again, formula here represents the volume of revolution. I rotate this region here over the y-axis. This calculation will give me the volume. And then from this one also, taking the differential derivative here, du derivative of x is 1, derivative of 1 is 0, so this is actually dx. And then let's transform this then. So I get the 2 pi here, and I'm going to leave the limits off for right now because I'm going to change those in terms of u. Let's make the substitution here. X plus 1 will be replaced by u, but I still have the x squared. But from this right here, solve for x, I get x is equal to u minus 1. So let's replace it here. So the x squared will be replaced by u minus 1. This will be squared. And then the x plus 1 is replaced by u, and then I'll write the square root as to the 1/2 power. The dx and the du are the same, so this will be du. And this is what I'm going to change. I'm going to leave everything in terms of u. I could transform it back to x and then use these limits -1 to 0, but I'm going to do this. These are limits of x. X equal -1 here on the integral, x equals 0. So if x is equal to -1, go back to this substitution here. X is -1, u is 0. So this changes to 0. If I'm in the u setup, that'll be 0. And then if I replace the x by 0 here, I get 1 for u. So this goes from 0 to 1. Now I can leave everything in terms of u, find the antiderivative of the integral, and then just plug in the values. So this is going to equal 2 pi, and go from 0 to 1. And then I'm going to do this on the side over here. This is going to be u minus 1 squared is u squared minus 2u plus 1. Squaring this right here. U squared minus 2u, and then multiply by u to the 1/2. So this will be u to the 1/2 times u squared. This will give me u to the 5/2. And then minus 2u times u to the 1/2 will give me u. Add the exponents, 1/2 and the u, this will be 3/2. And then u to the 1/2 times the 1 is u to the 1/2. So all I did is squared u minus 1 and then multiplied by u to the 1/2. Haven't taken the integral yet. Now we'll take the integral here. So this is going to equal to, we still have the 2 pi in front as part of the formula for the volume of revolution. So now I'm going to integrate here. Just basic power rule here for integrals. Add 1 to the 5/2 gives me 7/2. And then divide the coefficient 1 by 7/2 gives me 2/7. The next one, same thing. Add 1 to the 3/2 gives me 5/2. Divide the coefficient by 5/2. The same thing as multiplying by the reciprocal, so this will give me a minus 4/5. And then the next one, add 1 to the 1/2, we get 3/2. Divide the coefficient by 3/2. Okay, now we apply the limits here. So this should be evaluated then using the new limits of integration from 0 to 1. So still got the 2 pi out here. Evaluate everything at 1. So 1 to the 7/2 is going to be 1, u to the 5/2 will be 1, u to the 1 to the 3/2 will be 1. So all I'm going to be left with here when I plug in 1 is the fractional part here, the coefficient. So 2/7 minus 4/5 plus 2/3. And then you find your common denominator here, which is 105. Add up the fractions here, and you get 16 over 105. This turns out to be 16. Common denominator is 105. Add those up, combine. Get 16 over 105, and then that times 2 pi. So this will give me 32. That's 16 over 105 times 2 pi will give me 32 pi over 105. And that's, of course, cubic units. Thanks for watching. We'll see you next time.